Welcome back to ECE 442-542. Some announcements to begin. Office hours tomorrow, I need to slide 30 minutes later in the day. I've been double booked to our normal, but that's just for tomorrow. The other thing that I was made aware of today was the syllabus office hours are incorrect for Wednesday. So I've now tried to correct that or update that in the syllabus, and if you see the syllabus now for updated version of January 30th, you'll see that Wednesday's office hours are from 11 until noon. They are no longer what were originally published in there. I didn't realize that they were in error until everybody started showing up at the incorrect time. So hopefully that's now corrected, and if you need office hours, those are in the syllabus, and I believe they are correct now. But tomorrow I'm adjusting them just to keep you on your toes. They are switched or slid 30 minutes later into the day. They will be from 11 a.m. until noon. I guess maybe that's not so critical because your homework number 1 is due today at 11:59, but homework 2 is due quite soon. It's due on Monday, since our exam, first exam, is due a week from today. It's not due, it will occur 1 week from today. It will be due in about 90 minutes from now, 75 minutes from now, in a week. But there's also information on D2L. I hope you were able to find and access the video content and the lecture material for the 2 times that we were supposed to meet in person. It's provided for you on D2L. There's an additional piece that I've labeled as Lecture Video 2.1a, and that deals with the Z-transform of an exponentially damped cosine. On your homework problem, you'll not only need to work with that, but you may also be asked to derive an exponentially damped sine on homework number 2, and you should be able to follow that. The idea is you should be able to sort of duplicate the sine version along the lines of the cosine version without a lot more effort. That's the plan, and I hope that that lecture material for 2.1a provides that. In preparation for exam number 1, I don't know how many are interested in having a review session prior to exam number 1, but we would hold it immediately following next Monday's lecture. So that would go from 7 o'clock until about 7:01. We should be able to get enough material in that 1 minute for a review for exam. No. So it will last an hour, whatever. But if you have particular topics or questions, and this pertains to the online students as well, if you have a particular topic that you would like to address as a question during that review session, submit that into the particular quiz section on D2L. If you go to D2L, I don't use quizzes much in this class, but I do use them for your input to me. So it's not a quiz, but it's a way for you to submit a question or a topic that you would like to see addressed during the review session. But there is a deadline on that. It can't be Monday at 6:59 p.m. It's Sunday night, I believe, so that I can at least see those prior to the review session on Monday. Are you thinking you would like a review session? Show of hands, all of those online students. I want to see. Wow. So now I see those hands. I've recorded that, and I now need to see you attending on that evening. I've done this before, and I have about 1 or 2 students that I'm interacting with. Anyway, there is review material for exam number 1 also on D2L in the exam 1 unit. And just a note, if you are an online student, you need to make sure that you take the exam, and you have 3 options. You can take it either with Examity, and that one will still be a paper or a pencil to paper exam. You'll simply see the exam on the screen and you'll write your answers down on a piece of paper. Then you need to scan that and upload that to the D2L Dropbox if you're an online student. You may take it with a proctor, or you may take it on campus. Shh, keep that quiet since this is on YouTube. Nobody will see this. But you can come to campus, but you need to let me know. I need to have enough exams to cover that sort of overflow or student population of the online students. So you need to let me know, and you can let me know by submitting your desire to do that into the D2L Proctor Agreement Dropbox. All of that could just be filtered out from the on-campus students. You could have taken a 2-minute nap if you wanted to, but now your nap is over. Now that I should have cued you in to take the nap, right? Are there questions on exam 1 and what we will be doing? But the material, topic-wise, is really homework 1 and homework 2. Yes? So will we be allowed to bring an equation sheet? I'll try to tell you the process for exam number 1 next time. But if you look at a previous exam, you'll probably see a cover page, and I think you are provided with a table of Ztransforms, but you provide that, and you also will bring a page of notes, and that could be front and back of 8.5 inches by 11. And that page will probably be added to as we go to more and more exams. There will be 3 exams, midterms this semester, and a final. Did that answer your question on will you be allowed a crib sheet? You'll be allowed your own, and you need to provide or print out a table of Ztransforms, because Ztransforms will be on exam number 1. And today what I want to do is sort of finish up properties of the Ztransforms by talking about the properties of the Ztransform, and then we'll get into frequency response for discrete time systems. Hopefully you're familiar or remembering frequency response for continuous time systems. Bode plots. Well, we won't maybe so much be doing Bode plots for discrete time, but we do want to know how does our system behave or respond at a given frequency, and how can we find that? So we'll review the continuous time case and then develop the discrete time version. Let's then move into the first topic, which is just a few of the Ztransform properties, and I've given you a chapter from Sham's outline, from another Sham's outline, in the course resources section. I think well, I'm not even going to say what chapter it is, but it's a chapter from there on Ztransforms. It's also in the material that I've provided for notes on discrete time system foundations. And today we will just say, here's the definition, and we may use this script Z with the argument of that script Z being the time domain waveform x of n. And if we Z-transform that time domain waveform, little x of n, that gives us capital X of Z. That's the notation where capital X of Z is this infinite sum weighted by these z to the minus 1 weights. Z to the minus 1 raised to various powers. The first property is linearity, and you've seen this property with the Laplace transform. It's not new, it's just now we are seeing it for the Z-transform. If you now want to see what is the Z-transform of a linear combination of 2 waveforms, it's really just that same linear combination of the Z-transforms of the individual waveforms. What we will focus on in this class, maybe not so much in the first exam, but in subsequent exams, we want to be able to work with rocks. So I don't know if you knew this was a geology class or a minerals class. Well, it's the Gem and Mineral show, so we have to talk about rocks. But rock is now the region of convergence in this class. So if you see rock, that means region of convergence, and when we use the linearity property, that region of convergence could change when we combine different waveforms. And I've just given you a couple of examples, and I'm hoping that you run home immediately and start examining these. I don't have them all worked out. But one would be to look at the Z-transform of a unit step and then subtract from that the waveform associated with a one sample period delayed unit step. And I think you can see, hopefully, that f of n is just the pulse. It just ends up, f of n, if it's equal to f1 minus f2, f of n is just 1 at time n equals 0. And you could compare the region of convergence for f1, f2, and f, and you can see that they do differ. Well, not likewise, but a second example is if we had two exponential waveforms that we then linearly combined, in this case just added, and you can see then that the Z-transform of g of z, the sum of g1 and g2, the region of convergence actually is outside the largest pole of those two poles. You would have a pole at 1/2 and a pole at 3/4. The region of convergence for little g's Z-transform would be beyond and all the way to infinity the pole located at 3/4. And I think you should look at that a little bit on your own so that you understand what I'm meaning by if we do linearly combine two waveforms or more waveforms, if we need to know the region of convergence, it may have changed in that process of combining those time domain waveforms. And I think to allow you to appreciate that, you might examine example A and B on your own. I didn't really flesh it out here that much. That's why the question mark is there. But that's the first property, is the linearity property. The second property is everyone's favorite, convolution. But now convolution in the time domain is equal to the product of Z-transforms in the frequency domain. And that's why we like to play in the frequency domain, is because now we can simply do multiplication instead of having to worry about convolution. But convolution in the discrete time setting may not be quite as tedious, and we may look at that. I don't know how much we will go through convolution per se, but I think you are familiar with this from a previous linear systems class, 320A, for example. You should understand convolution. That's the second property, that convolution in the time domain looks like multiplication in the frequency domain. Third property is a time shift property, and this really just means delaying or advancing different waveforms and turning on those waveforms with the same amount of delay or advance. That's really what F times U signifies. In this particular case, if the amount of delay, little l, if we say n minus l for the argument in both F and U, then the Z-transform of that is going to be either an advance, if it's an advance of L units, or a minus L weighting on Z, or Z raised to that power F of Z. And I would encourage you again tonight to go home or sometime, and if you now have a generic F of n signal and this unit step is really being used as a window. It really just allows a certain portion of f of n to be turned on or switched on. That's how we are using the unit step, as a window or as a sort of switch, a turning on and a turning off of f of n. In this case, suppose that we delayed this exponential. Right now I'm showing this exponential going from minus infinity to plus infinity, which means in the negative time direction it's going off to infinity if we have an exponential that we're raising to higher and higher negative exponents. Usually we just think of the exponential response starting at time n equals 0 and going thereafter. Mentally, if you would just cover up everything in the negative time indices, that would be, let's say, a decaying exponential from time n equals 0 on up to infinity. If we now wanted to delay that by 2 time sample periods, and the unit step window slides with the same amount of delay, then we would really just slide that f of n waveform. How do I want to show this? If we delayed it by 2, where this is now u of n minus 2, do you see how we just pick up? In fact, in this case, the f of n would be shifted so that its normal 0 value is occurring at n equal 2, because then that would be f of 0, and we would turn it on with this yellow unit step that has been delayed by 2 starting at n equal 2. I would go home and sort of play with that and just make sure that you understand what happens when you have a waveform f and you're windowing it with the same amount of delay. Then whatever it looked like from 0 up to infinity, it looks the same. It's just it's now been delayed or advanced L units in time. If that's the case, then its Z-transform is obtained by the original function Z-transform, capital F of Z, weighted by Z to the plus or minus L, where plus is if it's advanced, minus if it's delayed by L units of time. The more interesting time shift property is when in fact there's really sort of a mismatch between how much the function is delayed and when we turn the window off or on. Suppose the window is turned on at time t equals 0. It's a classic unit step, which means that everything time index wise from n equals 0 all the way up to infinity is what we will see for the time domain waveform that we're trying to Z-transform. Which means if we had an exponential and we delayed it by 2, we would actually see f of minus 1, if that's our exponential, would be at time n equal 1, and f of minus 2 would be at n equals 0. And then everything else would be what we would normally see starting at time n equal 2. Well, because of that, then we have to make the Z-transform look a little different than what it does when the waveform and the window are slid, delayed, or advanced the same amount. In this case, we have the one you would think would be there, z to the minus L f of z, but this is like taking the derivative in the time domain. For a Laplace transform, we have to worry about initial conditions. We kind of have to do the same here, and those initial conditions can be accounted for by this summation from m equal 1 up to L, where L is the amount of delay, f of minus m z to the m minus l power. And here is an example of that. Suppose we wanted to here is L that I'm trying to highlight in yellow. And in fact, it's actually that particular index as well. But that's L is equal to 1. So it's confusing, I guess, because my L's and 1's look about the same, but my L in this example, I'm going to use sort of a script L, and the 1 just looks like a vertical line. Does that help? So that n minus 1 in this case, which is n minus L in general, L is equal to 1 in this example. Maybe I should have picked a different L, huh? But then I wouldn't be prepared to talk about that. But here is L equal 1. And in this case, then, there is your L value. L is equal to 1 in this formula. So if that's the case, we simply write this down. We know the Z-transform of little y of n, but if we simply identify or write down all of the terms in this finite sum, I'm summing from m equal 1 up to m equal 1, so it really just has one term. I replace little m with 1, and this would be sort of the initial condition that I would be picking up. I would pick up y of minus 1 raised to the z to the 1 minus 1, which that is actually just z to the 0, which is 1. Boy, I have a lot of 1's floating around, don't I? So that's just plus y of minus 1. And that's similar to, I think, what you should be remembering relative to your Laplace transforms when you Laplace transform a derivative. You have to subtract these initial conditions, and some of those are weighted by s. If we had a bigger delay, if L was 2, we might have y of minus 1 times z to the 1 minus 2 or minus 1 plus y of minus 2. Maybe I should have done that, huh? Oh, I've already... Oh, but I can play tricks with my paper, can't I? If I could actually do this. So what did I just say? Suppose that I now look at a different example with L equal to 2, so that now I want the Z-transform of y of n minus 2 u of n. And that should now look like z to the minus. If you wanted partial credit, you would just say, oh, the delay is 2, so that's now z to the minus 2 y of z. But now if we use those additional terms here, I'm summing from m equal 1 up to 2. I should see two terms. I have f of minus 1. Well, it's y of minus 1 times z raised to the 1 minus 2, so that will be minus 1 power, plus y of minus 2 raised to the z to the 2 minus 2, or 0 power, and so that z really doesn't even have to be accounted for. So that's what it looks like with L equal 2. So I did it. Thanks for the applause. And you can go ahead and applaud at home as well if you want. Then whoever is close by, they're going to be going, wow, what are you watching? Well, it's an ECE 442 542 video, of course. There's a lot of applause, both heard and provided, right? So here's property 4, scaling in the z-plane. And what do I mean by that? Suppose that we now look at z-transforming r to the minus n f of n. N, remember, is our time index. R is some number, but we're raising that to a minus n power. So if n is 0, we have r to the 0. If n is 1, it's r to the minus 1. Or you could think of this, if you don't like to think about negative exponents, you could say, well, that's the same as 1 over r raised to the n, f of n. So f of n is being scaled by 1 over r as the index n is sequenced. Meaning, if r is 2, then you can see that the original waveform f of n is actually scaled by 1, 1/2, 1/4, 1/8 as time evolves. So we're scaling the original waveform, and we're assuming that we know the Z-transform of little f of n. And we want to know what happens when we weight it by this 1 over r weighting, or we scale it. What actually happens? Well, you can see that this is now the Z-transform of f of n over r to the n. And in fact, if you know capital F of z, which is the Z-transform of f of n, everywhere you have a z, you simply replace it with a scaled z, and the scaled z is just scaled by little r, z. Suppose I try to work an example here. Suppose, maybe an example in general, suppose f of n is a to the n for n greater than or equal to 0. Based on, now you're going to have to be honest, do you remember what the Z-transform of a to the n is for n non-negative? It's killing me that you maybe don't just jump up and scream the answer. This was on a provided video. This a, if it's less than 1, this is a decaying exponential. This would be 1/2, 1/4, 1/8, etc. as n moves through time. Well, that's now 1 over 1 minus a, z to the minus 1, or if we multiply through by 1, where 1 is z over z, we might say, oh, the Z-transform of that decaying exponential, if a is now less than 1, is z over z minus a. So there's our given f of z, capital F of z. Suppose that now somebody says, well, I'm interested in the Z-transform of g, which is a weighted version of f. Meaning, now suppose that g is weighted by 1 over little r to the n, or this is now r to the minus n f of n. And that fits right into our property. What does that mean? We can immediately say g of z is equal to, if we use property number 4. How do we find capital G of z if we already know capital F of z? We replace every z that we see in f of z with the variable little r z. And here we're just having z to the first power, so that's not that challenging. It's now rz over rz minus a. Or if you factored an r out of the numerator and denominator, you would see that that's z over z minus a over r is another way to write, or an equivalent way of expressing g of z. And what I might encourage you to do, boy, I'm giving you a lot of pleasurable tasks to do this evening, aren't I? Take this home. Suppose you now, in this example, say let a equal to 1/2, which I've already sort of talked about, and let's say that little r is 4. So you might look at that particular example just to get a feel for this process of using or applying that property. Did I say that was our last property? I hope not, because I have another one. So property 5. Property 5 of the Z-transform, final, I bet you can complete the blanks. And if you couldn't before, you better be able to now. Final value theorem. This property says that if the Z-transform f of z converges, or it has a region of convergence that includes all values of z beyond the unit circle, and all poles of z minus 1, that factor times f of z, are inside the unit circle, then the following can be computed. The limit as n goes to infinity, or how f of n is going to behave as the time index marches off to infinity. What's f of n going to approach, or where is it going, can be found by simply allowing or computing the limit as z goes to 1 of z minus 1 f of z. And this should look familiar to you from the Laplace version of the final value theorem, where you had the limit as s goes to 0 of s times f of s. Here we're going to find that s equal to 0 is similar to z equal to 1. So s equals 0 in the s domain, or s plane, is similar to z equal to 1 in the z plane. That we will start to, I hope, that will become ingrained as we move throughout the semester. Questions on these properties? I'm looking for hands at home. Sorry I can't see, but I can't even see the hands in the room. Oh, I guess that can be solved. Still don't see any hands because I didn't leave my glasses on for very long, huh? That means that we can move on, not seeing any hands. Let's now look at the frequency response for discrete time systems. Now, how do you normally learn new material? I'm assuming maybe this is new for some of you. If you've had 429 or 529, digital signal processing, maybe this isn't new to you. But if it is new to you, maybe what you want to do is try to connect this with what you're familiar with from the continuous time setting, the continuous time frequency response. And that's what I want to try to do now, is convention. Let's have a convention. That's not what I wanted. I want to, I bet I can't put the glasses on. That won't help. If I can't read, sorry, you have no idea where this is going. Connection with previous knowledge. I would try to make a joke, but I know you wouldn't find it funny. You always find it funny. Well, this connection with previous knowledge assumes previous knowledge. Just saying. But hopefully you can go back and remind yourself, I didn't mean, that refers to me as well. I may have forgotten some of the previous knowledge that I should know. But what I want to do now is, how will a sinusoid be filtered by a low-pass filter? So now if an interviewer asks you this question, and they say, okay, I have a low-pass filter and I want to pass this sinusoid through it, what's going to happen? Or how will a sinusoid, in this case, how will a sinusoid be filtered by a low-pass filter? So you can give the default answer. It depends. Your interviewer, you kind of have to say that with a straight face, not being too, they may think, well, this person obviously doesn't want this position. No, that's not what you want to imply by that answer. But now what you want to imply is it really depends on the bandwidth of your low-pass filter and the frequency of the sinusoid. That's why it depends. How are those two related? If your sinusoid is much higher in frequency than your low-pass filter's bandwidth, then it will behave differently, or it will be filtered differently, versus if your sinusoid is in the pass band of your low-pass filter. That's what I'm meaning by it depends. All right, now let's go back to previous knowledge and say step 1. That was supposed to be a 1. That almost looks like a C, doesn't it? I have people over here critiquing my handwriting. Now I'm getting really sensitive. I'm going to have to bring my protractor to draw circles. But here, let's design a first order low-pass filter. Now, if you really wanted to get ornery, you would say it depends. What kind of first-order filter do you want? Here I'm assuming it's going to be a passive low-pass filter. We won't use an op-amp. So that we're going basic. And coming to class, I said we're going to be talking about filtering, and I was so overjoyed because I got the response back, well, that just means it's an RC filter. So hopefully everyone heard that comment, and now we have our RC filter, which is just a series combination, but we have a voltage as the applied sinusoid. That's our input, and our output is going to be the voltage across that capacitor. And we now need to figure out what R and C need to be in order to produce the low-pass filter that we want. But now we could verify or validate that, or if you're questioning, I don't remember if that's really how you create a low-pass filter or not, let me put that into the frequency domain. What's the frequency domain version of that filter look like? How does that picture change in the frequency domain? This is the time domain version. This is what you would build with Josie's parts. You would get a breadboard, try to ask for a capacitor and a resistor. Hopefully you could get one. But you would want to know the particular values, right? What's that look like in the frequency domain? I'll do the hard part. Four circles. No, structurally it looks the same. In the frequency domain, though, let me go ahead and replace those impedances with their complex values or expressions. The impedance of a resistor is just R. The impedance of a capacitor is 1 over SC. And now I want to find the transfer function between the input V sub I and the output V sub O. And there are many different ways of doing that. You could say, oh, let's just perform a voltage divider. And if that doesn't come back to you, that's fine. You can simply say, oh, let me just do this in a couple more steps. Let me apply KVL and find an equation for the output voltage in terms of my impedances and the input voltage. A voltage divider, though, would just be the output impedance divided by the sum of the two impedances. And that's now the transfer function between the input V sub I and the output V sub O. So that now H of S, if we wanted to, we could even rewrite that a little differently. That's now a ratio of ratios. Let's get rid of the ratios by multiplying both top and bottom by SC, and we end up with H of S equaling 1 over SRC plus 1, and this is now our transfer function for a low-pass filter. And if you wanted to, we could simplify that by just saying, oh, let's just call RC our time constant, tau. So this, you could refer to this now low-pass filter as having a transfer function 1 over S tau plus 1. And if you really needed to go find those component values, you would need to find an R and a C appropriate with the value of tau that we need to find for our time constant. That's now our transfer function for a first-order low-pass filter. Let's now create, let me tell you what kind of a performance requirement I'm wanting for this low-pass filter. Let's create a low-pass filter with a bandwidth of about 100 hertz. And the about is really just going to be, I'm going to probably approximate pi with 3, just so I don't have to carry around 3.14159. How many have pi memorized to? Okay, we may have to stand up and have a competition to see how many digits people know pi to, but again, maybe you can do that tonight at home. And that might influence who gets the more pieces of pizza or something. I don't know. Anyway, so let's now say that the cutoff frequency of our filter in hertz is 100 hertz. In radians, omega sub c, that's 2 pi f sub c, or 2 pi times 100. And that's now 200 pi, and now the about is, let me just approximate pi with 3, or now we're looking at a bandwidth in radians per second of 600. There's where the about is coming in. If that's the case, now we can look at the denominator of our transfer function for this first order filter, which was SRC plus 1, or that's now s tau, or tau s plus 1. That maybe is easier to say. Tau s plus 1. The poles of that transfer function are determined by the values of s that satisfy this equation, tau s plus 1 equal to 0. Or the pole, the single pole s, is now at minus 1 over tau, and we've now seen that we want that s to actually be minus 600. That allows us now to find the time constant of our low-pass filter to have a bandwidth of about 100 hertz. We now need tau to equal 1 over 600. That's our time constant. Or in terms of decimal values, you see how you can do all of this on a napkin and not even have to pull out your calculator during your interview? You now have this as 1 over 2 times 3 times 10 to the minus 2. And I remember what 1/3 is. That's about 0.333. And I can now divide that by 2. So that tau becomes 1.667 times 10 to the minus 2 seconds. That's my time constant. So for this particular system, what's infinity look like? When will the transients be gone from any injected waveform into this first order filter? What's infinity look like, roughly? 5 tau. So it's not very long, is it? It's pretty small in terms of infinity. So h of s is now 1 over tau s, but tau is just 0.00167 s plus 1. And this is now a low-pass filter with a bandwidth of about 100 hertz. What's the DC gain of that filter? If I put in 4 and then I waited an infinite long period of time, which is 5 tau, not very long, what would I see at the output of that filter if I put in a DC value of 5? How does the DC gain adjust that input voltage of 5? Or how do I find the DC gain of a transfer function? Or even does it exist? We look at DC relative to S. S equal to 0 is the DC frequency. That's 0 frequency. We evaluate H at S equal to 0, and we find that the DC gain is 1. What if we now wanted to verify this behavior or this design, verification of the low-pass filter in the S domain? And hopefully these steps we will start to see reproduced for the in the discrete time setting. Here we have our transfer function, capital H of S, is 1 over tau s, but tau was 1 over 600. This particular transfer function is in fact in time constant form, and that's a useful form for doing what? I'll give you a hint. Sketching what? Starts with a B. Bode plot. Boy, you didn't take much of a hint. All right, so what if I wanted to see the pole zero pattern of this transfer function? Where are my poles? Where are my zeros? I might like to look at this transfer function in pole zero form, and I can do that by multiplying by 1, not really changing the transfer function at all, but now I have 600 over s plus 600, and now I can explicitly see where my pole and zero are located by factoring or evaluating for the polynomials in the numerator and denominator the values of s that cause those numerator and denominator polynomials to vanish or to equal 0. This is now the pole zero form, and that's useful if we want to sketch the pole zero diagram. Let's say that we want to start by looking at the Bode plot of this first order filter. The magnitude of our Bode plot will sort of depend on where we have our gain, or what's our DC value, what's our DC gain of this transfer function, and we just convinced ourselves that it's equal to 1. This is our DC gain. And what does that mean if that is, I'm saying, is useful information if we're now plotting the magnitude of H in dB? What does a DC gain of 1 provide for us if in fact we are sketching the magnitude plot versus frequency, or the magnitude versus frequency, where the magnitude is in dB? If I have a DC gain of 1, what's the magnitude of that in dB? 0, because we just take 20 log of the magnitude of H, and at low frequencies the magnitude of H is 1. So we're starting at 0 dB for a magnitude. And now how far do I continue to go? This is really our log of omega axis. There's our independent variable. We're plotting the magnitude of H in dB versus the log of omega, so we can get a lot of frequency information in a short interval or horizontal distance. Do I go up or down with this, or do I just stay flat relative to this particular transfer function? At high frequencies, what's happening to H of s? If we let s, now we're looking at the frequency response. We're replacing s with j omega. If we now look at 1 over j omega over 600 plus 1, and we let omega go to really, really high frequencies, what's happening to H? It's vanishing, isn't it? It's going to 0. It's getting small. Well, we're plotting this in dB, so it's never going to finish, but it's going down. And what we can now do is say, oh, this is going down. And do I have to worry about the slope of that particular decrease of magnitude? Do I need to worry about changing that slope? And where did that slope, in a straight line approximation, where did this actually happen? What omega? That happens at 600. So this is now our cutoff frequency of 600. And what's the slope? it's minus 20 dB per decade or minus 6 dB per octave. Are we comfortable with what an octave is in frequency? What's a decade? Factor of 10. An octave is a factor of 2. So if you, did somebody say 8? No. There's 8 notes in an octave, isn't there? So you go C, then something else. What comes after C? D. You go all the way up to G, and then you start over, right? A, B, C. So there's 8 notes, and you have to worry about your half notes in there, your sharps and flats. You have black keys somewhere on that piano if you're playing that instrument. But anyway, an octave is if you went from middle C to the next C, that would be a factor of 2 difference in frequency. Middle C is not a very nice number, so let's say the A above middle C, or no, let's say the A below middle C. What's that? 220, I think, because middle C is about 230, 240 somewhere. So I think the A below, and you can correct me after the fact, but the A above middle C would be twice that 220, which would be 440. So the A above middle C is maybe what we're thinking about, and that's 440 hertz. I don't know, I'm wanting to listen to some music. It might be better than this lecture. But anyway, where are we? The Bode plot consists of what? 2 plots. Magnitude plot versus frequency and phase versus frequency. What's the phase look like? The phase plot. Where do we begin the phase curve for this low-pass filter? And where do we finish the phase? Where do we begin? At small values of frequency, when omega is equal to 0, what's h as a complex number? H of 0 is, it was 1, wasn't it? What's the phase of 1? 1 you can write as 1, or you can say 1 at an angle of 0. So we're starting at 0. At high frequencies, what's the phase look like? Now we have 1 over j omega over 600 plus 1. In the denominator, we have j omega. If we let omega get big, do you see that j omega over 600 will at some point start to dominate that 1? And downstairs, it will just be a j omega piece. So that now we have 1 over j, essentially. And what's that look like in terms of an angle? Well, j is 90 degrees. It's downstairs, so that's now minus 90 degrees. Our phase plot, if I could draw it, this was now at 600. So what I want to do is identify a decade before 600 and a decade after, and on a log scale, those are the same distance. Those don't quite look the same distance, but use your imagination. There's 0 degrees. This is now the angle of h of j omega, and this is now minus 90 degrees. And in our straight line, oh, that's supposed to be a straight line connecting 0 and minus 90. And right here at 600, this should be minus 45 degrees. This is 60, and this is 6,000. There is our Bode plot for this first order low pass filter. And the question,
do we expect Bode plots to be on the test?
do you expect to have Bode plots on the test? How do I answer that? Yes, it depends, huh? Probably not, but you should understand. I'm trying to get back to previous knowledge so that you have some insight into what we're trying to do for the discrete time case. So I hope that this is starting to look familiar. If it doesn't, don't stress out too much with this, but I hope that now what I try to provide is some insight into what I want you to be able to do. What I really want is if somebody now says, oh, I have a system described by a transfer function h of s, and you now have several of those from the homework. You have several plants that you've created. You've created several g of s's. You now might be interested in an input to that system and an output. In this case, our system is simply a low-pass filter, first order. Suppose that somebody says, oh, my time domain input actually looks like 2 times the cosine of 500t. Now I'm getting back to it depends. I've identified my low-pass filter's bandwidth, which is 600 radians per second. I've now given you a particular sinusoid with, what's the frequency of this sinusoid? In radians per second, what is it? It's 500. This is now the frequency of this sinusoid, 500 radians per second. And we can now go back here and say, oh, I now know how the magnitude and the phase of the output is going to be related to this input because I have the Bode plot, or I have the transfer function in my system. In our case, we could now say, oh, where is 500 on the log of omega axis? Let's just pretend it's right here. And we now know this is now omega equal, let's say omega 1 is 500. And from our straight line plot, how is the magnitude changed as it passes through this low-pass filter? Is it significantly altered, the magnitude, at the output versus the input? It has a gain of 0 dB. It's scaled by 1, so we should expect the output in magnitude to look about the same as the input magnitude. And what about the phase of the output? It's not 0 degrees, is it? It's now negative 40, something like that. So it's going to be shifted in time with a phase shift. It's going to be delayed by an amount in time consistent with a phase angle of minus 40 degrees. And we can say that with just a basic description. But if we wanted to compute it, we could say, oh, the sinusoidal steady state, this is after the transient, so after 5 tau, which isn't very long in this case, the sinusoidal steady state output is going to be what we started with in amplitude, scaled by the transfer function evaluated at the frequency of our input, which is J500, cosine. This is a linear system, so if we're shaking it at 500 hertz, after all the transients have decayed, our system is all going to be shaking at 500 hertz. And we adjust its phase, or we have a phase shift associated with the phase contribution of that low-pass filter at omega 1. Here's omega 1, here's omega 1, and here is omega 1. So omega 1 is wild in this because it's what? That's how we're shaking our system. We're injecting a sinusoid at a frequency of 500 radians per second, and after the transients have decayed, everything in that system is going to be shaking at 500 radians per second. If you wanted to find those values, the magnitude and angle in the S-plane, you could do that with an S-plane pole zero plot. We just looked at it from our straight line Bode plot. Here's the imaginary s, so here's another way of thinking of it. Here's the real value of s, and our pole is at minus 600, and the frequency that we're interested in, we're walking up the imaginary axis and we wait until we get to 500 and we say, oh, how does this pole or this transfer function contribute? Well, it contributes based on the length. That's going to be in the denominator, and it also contributes by the phase, and that's determined by the angle that that pole makes with this location on the imaginary axis corresponding to omega 1, j omega 1. Or we could say, oh, we can just evaluate that. I can evaluate or replace s with j500, and I can obtain a complex number. That's 600 j500 plus 600. That's the pole zero form, and this is now 600. And now I can insert my L sub p, an angle theta sub p. That's from the denominator factor, or this complex number, 600 plus j500 in the denominator. L sub p is the hypotenuse of that right triangle. The numerator we don't really have to worry about. This is now the magnitude of 600 plus j500. And what's the angle? What's theta p? How would I find that angle? Now we're going back to our trig. So remembering previous knowledge, we have to remember our trig. And what's theta sub p based on this triangle? The inverse tangent or arctan of opposite over adjacent. The opposite is 500, the adjacent is 600, so now we have the inverse tangent of the vertical over the adjacent. And that should be an angle less than 45 degrees, which is what our Bode plot told us. This is now 600 divided by 781 at an angle of about 40 degrees, which is what I said it was. So now this is 600 divided by 781, giving us 0.768 at an angle of minus 39.8 degrees. Or we can now write down our sinusoidal steady state output. That's 2 times 0.768, which is 1.536 cosine of 500t minus 39.8 degrees. That's now our sinusoidal steady state in the time domain. We put in a input of 2 cosine of 500t. The amplitude has diminished a little bit to 1.5, and we've delayed that by 40 degrees. That's the sinusoidal steady state output. Now what? I have to go and look at what class we're in, right? What is this class? It's definitely not a filters class. Well, it is. It's not a continuous time filters class, but we're in discrete time, and we now need to figure out how do we build a discrete time filter based on that example. We know how to do a low-pass continuous time filter. Can we use that information to actually build a discrete time low-pass filter? We actually want a low-pass filter in discrete time. what do we have? Well, we have v sub 0 of s, the output's Laplace transform, over the input's Laplace transform, and that was 1 over tau s plus 1. Or we can cross multiply, and we now know that tau s plus 1 times v sub 0 is equal to v sub I. Can I take that frequency domain expression into the time domain? And if I do, what am I looking at? How do I inverse Laplace transform s times the Laplace transform of v naught? What's s times a variable? What does that correspond to in the time domain? Derivative. So now we really just have tau as a constant. Now we have the derivative, the first derivative of our output waveform with respect to time, plus 1 times v0 of s in the time domain, that's just v0 of t, is equal to v sub I of t. And this is now a time domain differential equation. What's the order of that time domain differential equation? First order. We have one derivative. We now want to take that and find a discrete equivalent. We want to discretize this first order differential equation and create a first order difference equation. A difference equation in the discrete time setting, which can be done if we simply do a crude approximation of the derivative. Now we have to go back to our first calculus class and say, what's a crude way to approximate a derivative? What can we let the derivative of our output waveform be? This is just d v sub 0 of t dt. Can we let that be something? Isn't dv, that's a small change in the output waveform. What's dt? That's just a small change in the time domain. So we really have v sub 0, sample that, we could say this is n plus 1 times cap t minus v sub 0 of little n cap t. That's the dv. And our time, well, the small change in time is just n plus 1 cap t minus nt. Or what's that now going to look like in the bottom? What's the denominator? That's nt plus t minus nt. That's just t. So now we have v naught, and a lot of times we will simply suppress the sample period in our formula. That's now v naught of n plus 1 minus v naught of n divided by the sample period. What's our sample period? Do we have any way of knowing what that is? And this might be on the exam. If I gave you this differential equation, we know tau's 1 over 600. If I give you that first order differential equation and said, I need you to find a discrete time equivalent, or the sample period of a discrete time equivalent, what is capital T? This is now in seconds per sample How fast do we sample? And what can we use to determine that sample period? Do you remember a thumb somewhere, a rule of thumb? So now you're probably remembering twice the highest. Well, that's not what we want in this class because that's not fast enough. But do you remember we were saying, so twice is like the Nyquist. That's kind of slow actually for control purposes. What did we say our rule of thumb would be if we had a bandwidth? How fast would we want to sample if we knew the bandwidth? 30 times. What's the bandwidth of interest here? What was the bandwidth of our low-pass filter? Wasn't it 600? So our sampling frequency is 30 times that. And we'll pick up with that, but you can go home and try to find T. Here, boy. Where's T? You can find T from this information and then check it with what we come up with next time.